we're going to look at how to make a neural network. We're going to use a couple different tools online. The first tool we're going to use is Colab. So this is a Colab notebook. That means we can just do the code right on the web. We don't have to install anything, and we can use a GPU. It's great. If you've not used Colab before, you can just take a look at it. Google Colab. Let's take a look at Colab here, and you can just create a new Python 3 notebook. I've already started one. Runtime, that's something that we want to take a look at. We want to change the runtime. Make sure we're using Python 3, and we can use a GPU accelerator if we want. Why not? Okay, let's get into it. I'm going to just use TensorFlow version 2. If you have TensorFlow installed locally, if you're doing this locally, you don't have to do this line if you're already using TensorFlow version 2, but this is what you have to do in Colab. We're going to import TensorFlow, and we're going to use this MNIST dataset. If you haven't seen MNIST before, let's just MNIST example images. So this is kind of what MNIST images look like. They're just handwritten digits. So that's the data that we're going to look at right now, and we're going to try to categorize them of what digit they are. Okay, let's make that happen. All right, we have that information. Great. So let's just take a look at what's the shape of the training set. There, 60,000 training examples, and they are 28 by 28 images. Okay, and let's look at what the shape of our what we're trying to do. What y is. So we have 60,000 of those, which is good. This is the same. And let's just take a look at a few of them. So yeah, what we're trying to predict is what digit x is. So the first digit's 5, the next one's 0, 4, 1, 9. Okay, let's just get right into it. Let's make ourselves a model. One way we can do that in TensorFlow using Keras is the sequential model. It's one of the easiest ways of doing it. And for our first model, that's what we're going to do. We're going to say tf.keras.models.sequential. And whoops, I'm going to do that. We are actually going to put stuff in that model. So the first thing I'd like to do is you add layers to models in Keras. I'm going to add a layer called my input layer. And all my input layer does is it defines what the shape of the data coming in is. And we happen to know that the shape is 28 by 28. So I'm just going to define that. I'm going to add another layer. So the next thing I want to do is, it would be great if we process this image using, convolution because it's an image, but I'm not going to get into convolution in this video. We're just going to flatten that data. And there's a really easy called flatten. It's a layer. So it's going to take this data, it's 28 by 28, and it's going to turn it into 784 data points instead of 28 by 28 data points. Okay, this X training data, the values are probably not within 0 to 1. which is what neural nets really like as input, is 0 to 1. You want to normalize all your data. We could do that up here, and that's probably a better way of doing it, but heck, we can do that right in our neural net. So there's this thing called batch normalization, and that'll just normalize the data for us coming in. If we should do some data science and take a look at that data, and maybe not all of it should be normalized the same way, or normalization is probably not the right thing to do, but we're just going to say that that's the situation in this case, and actually it is. So we have this sequential model. What's happening is we get our input, we flatten it so that it's not in an image anymore, it's just in a line of data. We're going to do a batch normalization. We haven't actually done anything interesting to that data yet. We're going to make our first dense layer. Okay, so this dense layer, we're going to tell it how many units that we want it to have. And I'm just going to make us output a dense layer right away. So this is going to be our output. No hidden layers, just an input layer, and then we're going to go right to a dense layer. And we'll see that that actually works. I mean, not well, but it works. And for our activation function, activation functions are really tricky. Not really tricky. I mean, they're important is what I mean. So we know our output is categorical. It's 5 or 0 or 4, and that's categorical. And because our output is 5 for the number 5 and 0 for the number 0, that's called a sparse categorical input. And that's different than sparse for 5, or sorry, for the number 3 would be 3. But what we're probably going to output here is a probability field. We're going to output 10 different values. So our non-sparse for number 3 is going to look something like this. It's going to be 0 probability for the number 0, 0 probability for the number 1, 0 for the number 2, full probability of 1 for the number 3, 4, 5, 6, 7, 8, 9. So this is what our neural net is going to output. It's going to output a probability field of how probable it thinks each number is. So the first spot is for the number 0, second spot is for the number 1, 2, 3, and so for the number 3, it's going to say that there's 100% probability. Well, that's what we want it to do. So we want an activation function that helps us do something like that. We could do something like, we could use sigmoid, or we could use, I'm obviously saying the wrong thing. Let me just get to the right thing. What we want to use is softmax. So activation function softmax. What softmax says is that I'm going to put a soft maximum over how much all of these 10 output neurons can fire, such that the total has to be 1. And if we look here, that's what happens here. We're saying that there's a 100% chance that it's 3 and 0% chance that it's everything else. But our neural net, if it output that it's 99% chance a 3 and a 1% chance a 9, we would say that actually it did pretty well. It categorized it as a 3 successfully with pretty high accuracy. And the softmax just says that that probability, 100% probability, or out of 1, has to sum. Okay, so that's our model. We just made it. We just defined our model. And we could do something like model.summary to tell us about that model. and it tells us how many parameters are used in each layer, and we could get and what the input and output shape of it is. So let's just get rid of this, and let's go back and say model dot. We have to compile it. So what does it mean to compile a model? Well, we've only defined the steps for our neural net, our model, our neural net to do. What we need to do now is we need to tell it what kind of functions to use to train it. And that's what we compile it. So one of the things that we need to tell it is what optimizer we're going to use. And there's a wide variety of different optimizers. Atom is like this pretty nice, well-balanced optimizer that does a whole bunch of nice fancy stuff. And the simplest optimizer you could use is stochastic gradient descent. So we're just going to use a simple one, see if it works. And not only do you have to tell it what kind of optimizer you need to use, you need to tell it what your loss function is. Let's just get back to optimizer for a second. If in doubt, use stochastic gradient descent. It's pretty good. It works. It's the most basic one. If you want to try to be fancy, you can use Atom or look up the other optimizers. The loss function. Okay, so your loss function is how your expected output and what your actual output is, and how to use those. In this particular function, this is a tricky one. You actually have to know that it's a sparse categorical loss function. And I can't quite remember what it is, so let's look it up. Tensorflow Keras loss. Yeah. It is sparse categorical cross entropy. Yep. That's what we want. So it's sparse because our input here is just the number, just the category. It's the 5th category, the 0th category, the 4th category. The 4th category happens to be the number 4. 1st category has to be the number 1, but that's our sparse category. And we want to use cross entropy. So cross entropy and softmax work well together. It's kind of beyond this video to get into all the different loss functions, but this is a particular loss function that you use in this situation where you have a sparse category coming in and you want to use softmax over your output probability field, and we can output some metrics too. And your metrics always have to be in a list, and we're going to use accuracy. Okay, so then after we compile the model, we can fit the model to the data. Actually, let's just run that. I'll show you what that does. There you go, it's done. Model.fit. So now we're going to say that we're going to fit the data to the model using everything that we've told it how to so far. Train, and y equals y train, and I think that's all we got to do. And it's just going to do it for one pass through the data. If you want it to go multiple passes through the data, we call that epochs or epochs. Depends which country you're from, and we can say, hey, do it for 2 epochs or epochs, or however you want to say that. All right, look at that. So I'm not going to get into what the loss means, but usually lower is better. but something that is a little bit more understandable for us is the fact that it got to 85% accuracy and 89% accuracy on the training data. Never trust your training data. That's why we have test data. So let's see how well it did on the test data. Model dot evaluate, and then we can say x equals x test and y equals y test, and let's see how well it does on the evaluation. 91%. That's actually pretty good for this really bad network with no hidden layer. There we go. We made our first network. We trained it. We tested it, evaluated it. Let's have it make some predictions. So let's first take a look at the test data, and let's take a look at the first 5 numbers. So in the test data, the first number is 7, and then 2, then 1, then 0, then 4. So let's predict the test data. So we use our model and we say predict, and we're going to feed it x test, and I'm going to feed it the first 5. That should work. Great. And so I can say p test and print that out. Now it's not going to look like this, and I'll get to that in a second. And it's going to look like this, because remember, we're outputting probability fields, not the actual classification. Okay, so what could we do? Well, we could say ptest.arg max, and I think I say axis equals 1, and there we go. So these were the highest values for p-test. So let's take a look at what those were. Max axis equals 1. So it said that there was a 99.7% chance that it was a 7. That's what it's predicting, that it thinks that it's 99.7% sure that it was a 7, 99.6% sure that it was a 2, 97.2% chance that it's a 1, 99.99% chance that it's a 0, and 94% chance that it's a 4. All right, there we go. We created a super simple neural net. Now this is it doesn't even have a hidden layer. And it's about as simple as you can get for an image, and not have any convolution and actually do something. And then we compiled it, we fit it, we evaluated it, and we looked at some of its output. Some of the test data, to see what categories it was, and then we made some predictions using our model. And our prediction, just so happened to predict exactly the right classifications, which was great. But we know that it's 91% accurate, so it's going to get like 9% of them wrong. We just happened to get all the ones correct. And then this told us, then we can say, what its reported confidence level is for the predictions that it made. All right, hope you enjoyed the video. Take a look at some of the other videos I have. I'll see you in the next one.